third possible structure that you can see. So you have a planar transform, you have a non-planar cis form, and you can have a non-planar transform. The non-planar transform has not been observed conclusively. These two have been seen, but the non-planar transform people have seen come in melts using Raman spectroscopy because there is a principle of mutual exclusion, that comes in handy in these cases, and therefore people have said this might be existing and so on. We didn't even bother to look at that at that point in time. We were trying to do some other experiment. All we were trying to do was the following. We took the cis forms and we excited it with a laser to get it to its first excited electronic state. In that electronic state, what happens is the cis is this way, okay, and the trans is this way. The excited electronic state has a form in which the benzene is this way. So it is actually in between these two. So in fact, the structure has to go from this to the transform, cis has to go to the trans. It actually has to do this, it goes here, and then to the other form. And this is the structure in the excited electronic state. So if we excite it to the excited electronic state, and then the molecule returns to the ground state after a few nanoseconds or sub-nanoseconds, what will happen is the molecule has two chances. It can either go here or it can go here. So if you now excite this to the first excited electronic state, and then see what happens, you will actually see both cis and trans in this happen. So we are actually converting a cis form to a trans form to an electronic excitation. Cis and trans can't be easily converted, The energy for conversion is enormous because you have to break a double bond and get it over. But in the excited state, what really happens is you are taking this pi electron, putting it into a pi star orbital, reducing the bond order, molecule has this structure, and then when it comes back, well, it has a probability of this or this, and therefore you will get the other one also. So, you should get this. And this again, people have seen this, it has been beaten to death, and everybody knows that through a photoexcitation process, you can convert cis to trans and trans to cis. Of course, you can take the trans form, again the same excited electronic state, and then it can go one way or the other, and you can get either of these. So you can convert cis to trans and trans to cis simply by a process of an electronic excitation. So we thought of doing this for a very different reason, which I will get into. The reason was too stupid to talk about now. But we came up with something very interesting. And what was that? The molecule went from this state to this state, but it also went to this non-planar trans. Because now it can go from here, it can go to this, it can go to this, or it can go to this non-planar structure. This non-planar structure being not very stable, what happens that under normal conditions is it immediately goes to the planar form. And that's the reason why people are missing it. But the cage of it comes in very handy. This guy goes to non-planar form, the cage piles up, and this guy then suddenly realizes he's in the wrong place. He should be going to the planar form. It sees the non-planar trans already, the planar trans structure out there, but it can't get there because there's all these argon atoms surrounding it. So the cage effect essentially comes in very, very handy for us, and we can therefore produce this structure. So here is my trans, and here is my cis, and that's the only difference. Non-planar trans is there somewhere. We don't know whether it is up here or up here. That is not known. Our experiments clearly showed that the non-planar trans must be somewhere out here. That's the higher energy stuff. And therefore, here is the potential in the diagram. The cis form, the trans form, this is the global minimum, this is the local minimum. And that's the excited electronic state potential curve. All schematic, they're not real. So all I'm trying to do is to go from here, I jump from there to there, I get back to the state, and then it can go here or here, I can get trans this, but then there is another, along the other coordinate, I have the non-planar trans. The molecule from here can jump into this minimum, can jump into this minimum, or it can jump into this minimum. But once it jumps into this minimum, under normal conditions, it will jump back to this transform because that's the most stable. But the cage effect essentially is preventing that from happening, and therefore it gets caught in this non-planar trans. And how did we know that? Well, when we record the spectrum, here's the spectrum for the cis, the trans, the spectrum for the cis. This is the photo irradiated cis, and after leaving, we got this. But if you look at this, there are some places where I put an asterisk. Those don't occur here or here. They are all new features. And we therefore sat down to figure out what these new features must be. So we went back to calculation, we took the non-planar structure, we calculated the vibration frequencies for this, and lo and behold, it matches beautifully with all these star structures. Meaning that what we have actually done, and of course, we then subtracted all these things out and we got the spectrum out here. And here is the spectrum for the non-planar trans, and you can see that there's a pretty good match between the observed spectrum and the computed spectrum, telling me that what we essentially have done is taken the cis form, photo-excited it, and then it returned, it gave me cis, it gave me trans, it also gave me a non-planar trans, which has been eluding us for quite a while. But the cage effect essentially came in very handy, stored the non-planar trans in its form, and then we were able to actually see it. If you anneal this matrix, meaning I just warm it out and then bring it back, what happens? So it flips back to the planar form, because the energy difference is so small, the barrier is hardly anything. And the 30K, whatever KT that you are giving, is more than sufficient for the non-planar to go to the planar, which therefore told us that the transform must be the lower energy form and the non-planar trans must be somewhat of a higher energy. This is another experiment that people did. You take ICN, and here's the cage, R1, and you shine light on it. It becomes I plus Cn, the IC bond breaks. Under normal circumstances, if you do this in a gas phase, the Cn would just say bye-bye and go away. It won't react. But here the cage effect just keeps it. And therefore what can happen is the Cn will now start to rotate in the cage. And when it rotates, it all depends on when it decides to hold back the I all over again to form this molecule. If it holds the I under this configuration, what you would have done is produce the INC, that is it. So you can start from IC and the cyano compound and get the INC compound. This has been observed. And why is this happening? Because the cage is preventing the fragmentation products from going away. It's keeping it there and saying, no, look, whenever you can, please react and see what I can get. And in that process, what really happens is you can get isomerization going on. Because during the process, the time between the bond has broken and the bond has formed, the fragment will be rotating. And when it rotates, it all depends on when it gets back to form the bond. And when it gets back to form the bond, it could either give back the ICN or it can give you INC. And therefore, you will see that if you start with this compound, a little while later, you will get a mixture of IC and INC. Try doing this in the gas phase. When it dissociates, it just goes away. You will not see this isomerization reaction. There is no cage effect under those conditions that can keep this going. The last example I am going to give you, this is just to tell you this is the work of other people. We have not been doing this, but excepting for the ICN, everything else that produced what we have done. The ICN is an example from the literature. This is an example from the literature. And what essentially has been happening here is this is a cyclodextrin. Essentially, it's a bunch of glucose molecules that have been put together. And you have three types of cyclodextrin. You have alpha, beta, and gamma, depending on, say, you put 6 glucose molecules, 7 glucose molecules, or 8 glucose molecules. And what it does is, it essentially increases the circumference. Now, this molecule, in slightly 3 dimensions, will actually look like a bucket. So, like an engineering drawing, I have shown you the side view or the top view or all that. So this molecule actually looks like a sort of a bucket. And what you can actually do is use this bucket to bring this cage effect into play. And by going from alpha cyclodextrin to beta cyclodextrin to gamma cyclodextrin, in which I am essentially increasing the number of sugar units from 6 to 7 to 8, all I am doing is increasing this bucket size. The bucket is sort of a larger amount as you go from alpha to gamma. Here is one reaction that people have done, because I have shown you the person who has done the gamma routine has been New Orleans or something, and he has done a hell of a lot of work with photochemistry and cyclodextrin matrices. This is one of the cyclodextrin compounds. So if you take this compound, and of course X can be oxygen, in case there is going to be an ester, and then you photolyze this, and then of course you can have this guy sitting back on the ortho position, or it can go to the meta position, or it can simply go away and give you the RCOH and the phenol. All these are 4 possibilities. If you do it in methanol, you get 48% of this, 30% of this, 14% of this, and 8% of this, meaning that the reaction can actually choose to undergo any one of these channels. One channel is substitution or rearrangement with the ortho position, rearrangement with the para position, and complete dissociation. And this can happen. You do this in other solvents, and this again happens. But you do this reaction in a cyclodextrin medium and see what happens. You get 99% of the meta ortho form. You get hardly any para form, and you don't get any dissociation product at all worth mentioning. Why? Because this molecule actually goes into this bucket, and And when it goes into this bucket, this guy is exposed to the ortho position, and therefore it can jump to the ortho position and form a compound. If it has to come and form a compound in which the para is substituted, what should it do? It can't go through the bucket. There is no space. You don't have to come all the way around and then come here. But the bottom size is also quite small, and therefore the para is actually kept quite hindered. It's actually kept quite insulated, and therefore the bottom of the bucket prevents the molecule from getting in. The para portion is completely insulated, and essentially what you have done is you have used this cyclodextrin as a cage in which you are selectively allowing one part of the molecule vulnerable to a reaction and keeping the others away. Also, what you're trying to do is this cage effect prevents the molecule from going away, because the moment it forms a dissociated product, it is still within the part of within the confines of the cage, and therefore it doesn't go away. It immediately jumps over to the ortho form, and therefore you get 99% of the product, which is ortho, almost negligible amounts of para, and nothing of at all what the dissociation starts. And this is something that is done at room temperature, and therefore you can see that you don't have to get to 10 Kelvin and start using the cage. You can actually use cages under room temperature conditions. Yes, Vijay.
So what if the cage inverts, or is the molecule just thrown out of the cage in the case of room temperature? Because there might be certain excitations by which it's just thrown out of the cage.
The cage has intermolecular forces within it and outside it. The cage actually is hydrophobic on the inside and hydrophilic on the outside. And where the molecule gets in, it's the hydrophobic part that we want to get in, and those interactions will keep it stable only. And that is what retains the molecule for a sufficient length of time so that the reaction can happen. If the molecule gets expelled out, then of course it's a very poor cage. And so if we had molecules extremely polar, they would refuse to get into this cage, and therefore you would find the cage in those cases would not really act as a cage, where the molecule will try to avoid the cage. Just like the lion would have tried to avoid the cage if you ever showed it one. So this is basically the effect of a cage under room temperature conditions, where you can essentially alter or tune the reaction channel. There are three possible reaction channels, and you are essentially forcing the molecule to pick up one reaction channel simply by providing the cage effect. So I think it's just about time to wind up. So what can cage effect do? It can lead to a very different reaction group compared with that in the gas phase or under unconfined environment. And of course, if you go back and look at chemistry, there are innumerable number of examples when you see the cage effect dominating and showing you something very, very different than what you see otherwise. Now, all I have done is just introduce you to thinking about cage and given you a few examples, and it is not even the tip of the iceberg. It can result in some very unusual structures being stabilized. Like I told you about the non-planar trance, the cage effect actually supported that structure and kept it there for us for we could go and look at it. And that's again the nice thing with the cage game. Thank you.
Questions? Anybody has any questions? So let's thank Professor Vishwanathan for this talk on chemistry in cages.